So I'll move to the next topic, that is called queuing models. Okay, that is called queuing models. So what is it basically the queuing model is? So queuing theory. Okay, so if we talk about industrial engineering, etc., and all, this itself had a scope of coming it as a single paper. Okay, so we will be just discussing what is queuing model is, and out of plenty of models are available in that, the basic and the minimum one we will be touching in this subject. Okay. So what is this queuing model is? What is its need, or why you want to study this queuing model? Tell me. Any idea? So basically this deals or discusses about the queuing patterns, the queue patterns, the queue behavior. Okay, and if you might have seen the queues in various stations, railway station, banks, post offices, etc., cinema theaters, etc. So the people's behavior in each place is going to vary. Okay, the queue size is going to vary. The arrival pattern in each of this is going to vary. Okay, if you talk about theater, so theater only at the time of the show only the queue is going to form. If we see the bank, so from morning to evening the queue will come. Okay, theater queue, there is a restriction is there. Hospital queue, there is a number of tokens is restricted. In bank, no such restriction. So based on the time period and availability, you will get the service. Okay. So the arrival, the so how to compare or how to classify the arrival patterns. Okay, how to differentiate the service pattern, the service mechanisms, the behavior of queue, and certain cases you will have priority customers will be there, they will be entering in the queue. So in that case, how that priorities can be given. Okay, like this you are studying the entire behavior of a queue by using the various queuing models. Okay, so queuing models definitely will have the information about the arrival population. So based on the conditions, the arrival population sometimes may be limited. Okay, sometimes the arrival will be random in nature. So how to differentiate these all terms? Then there are types of queues will be there. So based on the service mechanism, sometimes on a queue you will be straight away going to a counter. Okay, so there no other shifting is there. So wherever you are standing, however it is going forward, you have to go forward in that direction. Okay, so single queue, single server system. There are multiple servers will be there which will be handling from a single queue. Normally you might have seen in the case, the first model you can see in the case of railway stations, etc. The second model, you have multiple servers and but queue is only one. So in bank, if you are going, so they will be giving you the numbers or slips, and you have to wait at some location. According to your service number, you will be advised to go to the service mechanism. So it is a single queue, multiple servers are there. And then in this itself you can see when you are taking the token from a bank, they will ask you about what service you want to do. Okay, are you going for passbook printing, or are you going for depositing, or are you going for any loan purposes? So according to these criterions itself, the queue token numbers are going to change. Okay, so the priorities they are providing in the bank. So single server is there, multiple server is there, and sometimes in the railway station, okay, the queue length is long. So what the railway authority will do, they will just start a new queue, they will just form a new service mechanism instantly. So what the people will do from these two queue, they will try to go to that queue. Some people will go to that queue, some people will remain here, some people will jump from one queue to the another. Okay, some people will say that we'll wait in a queue for some period, and then they will say that no, I will not get the service, so I am not being part of the queue and leave. So these kinds of behavioral study, that is also a part of the queuing theory. So there are terms like jockeying, balking, ranging, etc. So to study about these kinds of changes in the people when they are in the queue. And you will have single server, multiple server, single queue, multiple queue. So based on all this information, what your thing is that if that is in a bank or in some places, is the capacity of one server, is it sufficient? Okay, do I want to go for a second server? Okay, that is a second person has to be done or not. So is the service time is up to the mark? So these always you can able to study the system or a queue system. That is what is basically you are doing in the queuing models. Yeah, so this is already I have discussed. So queuing theory is the knowledge dealing with waiting lines. So waiting line models consist of mathematical formulas and relationship that can be used to determine the operating characteristics for a waiting line. So they help in making decisions on the amount of capacity to be provided to give the desired service. Providing too much service involves excessive cost. Providing too little service causes poor customer satisfaction, idle employees, etc. So you want to achieve an economic balance between cost of service and cost of associated with the waiting for that service. That is what basically the queuing theory will do. Okay. So now you can see over here. Now you can see these are the queue. So these are the calling population. Okay, the calling population or the arrival population. So this sometimes will be finite in number. I have a if in the case of a doctors, the number of tokens are restricted. This much patients only a doctor will see on a day. So the tokens are restricted. So the population, there's a finite. But when we talk about in the case of railway station or in the banks, the arrival rate or the arrival people are not in finite number. They are infinite in number. Someday it will be high rush will be there. Someday there will be only very rushes available. So according to these situations, you can see to that you can see here only one server is there for the entire queue. Sometimes there will be a one more counter will be there. So if more counters are there, we call it as multiple servers. And this is a third customer. He finishes his job and is leaving. So to study this entire behavior of how this systems looks like and has to propose a balanced model, okay, between the customer satisfaction and between the effective utilization of the server. That is what you are basically checking in the queuing model. So this is what I told you, structure of a waiting line system. This is called, the first is called single channel. There only one system is there to serve. Okay, this is the one system to service. Here only one queue is applicable. So people comes, do the service and they leaves out. Here multiple servers are there from a single queue. Okay, multiple servers from a single queue. Okay, so three servers are shown over here. They are taken from the queue. So according to their priority, they will be given the service. So this is our symbol. Then you will have parallel, you will have series systems. Okay, and sometimes the priority systems will be also will be there. So there are plenty of models are also available in the queuing condition. Yeah. So the key characteristics of these are the key characteristics of the service. One is distribution of arrival time. How or how much a customer is arriving on an hour. Okay. Are they finite in nature or are they infinite in nature? So that is what is basically the distribution of arrival time means. Then distribution of service time. So how much time does it requires to serve a customer? Is it a constant one or is it a variable one? That's the second thing. Second is queue discipline. Okay, so there are queue disciplines are available called as first come first serve FCFS, last come first serve LCFS, service in random order SIRO, and then they are called priority customers. So that is service in primitive priority and random priority. So these all things are there. And how is the server characteristics are. So totally in this, this all are associated with the time, and time normally that is going to be in the case of distributions. Okay, so normal, Poisson, so these kinds of distributions are normally used to represent the arrival and service patterns here. Yeah, so we were discussing about the queuing model in the yesterday's class, and we have seen how the various types of queues we have discussed, and some of the waiting lines also we have seen. Okay, so this is called the multiple server condition. This is called as a single server. So this is multiple server single queue. This is single server single queue. Okay, so likewise these all things we have seen in the discussed in the yesterday's class, and as I told you, the important characteristics of a queuing system will be the distribution of arrival time, distribution of service time, queue discipline, and server characteristics. So distribution of arrival, the manner in which the customer arrived, distribution of service, the time required for service, queue discipline, so priority or normal priority. So we have discussed yesterday. And we will have server characteristics also. So these are some of the queue disciplines which is commonly seen. So you can see first come first serve as FCFS. You will have LCFS. You will have LCLS. Okay, and you will have then you will have priority rules. Okay, so we are not going to that into the deep. So the queuing system, so it is basically a three-part code. So A bar, B bar, K is used to describe the various queuing system. So that is A is the arrival distribution, B is the service distribution, and K is the number of channels which is used for the system. So basically this is not a three notation. Okay, so basically that is basically that will normally write in terms of notations. Okay, so that basically you can see you will be connecting it from a six letter terminologies. Okay, I'll just give you its details. 1 minute. Now that will be normally represented by like this. Okay, so any queuing model if we see, so that will be represented as inside the bracket. So queuing, so Q U queuing model. So that will be represented as A/B/C is to D/E/F, and this representation that is called as Kendall's notation. Okay, so this is called as Kendall's notation. So sometimes it will be A bar B bar C is to D slash E. F is an optional one. Okay, F is an optional one, and A corresponds to, okay, here the A is corresponds to arrival distribution. Okay, so arrival distribution. So arrival distribution means it is inter-arrival time. So okay, so that is inter-arrival. Okay, that is how the customers are arriving. Okay, are they arriving at a constant rate, or are they arriving at an infinite rate, etc. So that's the way. Or in an hour, how many customers are arriving? So that is the notation A that deals with arrival distribution. So B is the departure distribution. Okay, B is the departure distribution. So when a customer will depart, when after his service is over. So in another way, that is also called as service time. Okay, that is also called as service time. The time which he requires to spend in the system to complete his task. So the next term C. So C is basically number of parallel service channels in the system. Okay, C is called number of parallel service channels in the system. Or in another way, I can say that the number of servers in the system. Okay, the number of servers in the system that will be represented by the letter C. Okay, and the next term D. D is maximum number of customers allowed in the system. Okay, so D is maximum number of customers allowed in the system. Okay, whether it is a finite population or whether it is an infinite population, that is basically the letter D describes or discusses. And E represents your service discipline. Okay, your service discipline. So service discipline. And F is the size of calling source. Okay, F is the size of calling source. Okay, so this is what is basically the meaning of the Kendall's notation. This is how normally a queuing model will be discussed or queuing model will be described. So based on this Kendall's notation, you will have plenty of queuing models is available. Okay, plenty of models will be available. Okay, so we will be dealing with only one model, only one particular model in that in that case. That will be M bar 1. Okay, so that will be inside the bracket M slash 1. Okay, is to infinity slash FCFS. Okay, where if we see, so the terminologies are similar. So this is letter A, this is B, this is C, this is D, this is E. Okay, so A, B, C, D, E is to will come in between. So what is that first M? M corresponds to. What is that letter M corresponds to? What is that M corresponds to? So M corresponds to the Markovian property of the exponential distribution, or I can say that the inter-arrival time, okay, the exponential distribution of inter-arrival time or Poisson distribution of arrival rate. The first M corresponds to. Okay. The second is also the service time. So service time is also exponentially distributed or it is Poisson distributed. So the M corresponds to the Markovian property of it. And the one number of parallel service channels in the system, we have only one server is available in the system to take care of the people. So it is a single channel. It is a single channel queuing model. Next is D. D is maximum number of customers allowed in the system. So that is marked as infinity. That is, there is no restriction on the arrival size or pattern. Infinite number of people are allowed in the queuing system. And FCFS. So FCFS means whoever first is there in the queue, he will get the service as and when the service channel is free. Okay. So this is what is the basic queuing model that we will be finding that using this model we will be finding the solutions related to the waiting time, related to the service times, okay, server utilization, server busy, customer waiting in the system, customer waiting in the queue, okay, and the length of the queue, the length of the system. So these all things we will be solving based on this first model. M bar 1 is to infinity slash FCFS. So this is basically we are deriving from the Kendall's based on the Kendall's notation. A bar B bar C is to D slash E slash F. And based on this, you will have plenty of models. So some of the models like M bar 1 is to infinity slash SIRO, M bar 1 slash N slash FCFS, M bar S is to infinity slash FCFS. Likewise, you will have up to service level cost model, 7-8 types of models are available. Okay, so we will be discussing only with respect to the first model only we will be discussing. So I'll just go back to the PPT again. Yeah. So we have seen the three part of the code. So A slash B slash K. Okay, A is the arrival distribution, B is the service or departure distribution, K is the number of channels in the system. So after that you have to put is to and then you have to write the next D bar E or D bar E bar F. Okay, depends. So in that notation that is called Kendall's notation, and the terms which normally comes under this is M. We have seen it already there. M, D, G, etc. Okay. So M stands for the Markov distribution, that is Poisson or exponential. D stands for deterministic, that's a constant value. G is a general distribution with a known mean and variance. Okay. So this is already I have told you M bar K is given, refers to a system in which arrivals occurs according to the Poisson distribution. Service time follows an exponential distribution and there are K servers working at identical service rate. So the K I have replaced as 1 in our first model. So there is only one server to look after the customers. Yeah. So M bar 1, M bar K, M bar G bar 1, M bar G bar K, etc. Okay. So these are the terms which associated to A slash B slash C. Then you will have is to D slash F. So D is the population is finite or infinite, and the E corresponds to what kind of a queuing discipline is being followed, whether it is a FCFS, whether it is LCFS, or whether it is SIRO, etc. I hope the things are clear right now. So this is our first model, as I told you, M bar 1. So single channel, single server, Poisson arrival rate, exponential service time distribution, first come first serve queue discipline, unlimited maximum queue length, no bulking, infinite calling population. So these are the characteristics of the queuing model that I have written over there. So these are the probabilistic value. Okay, these are the probability. So the solution. So we are not going to derive anything. So this is the way you have to memorize some of the equations. Okay, for solving these problems. Okay, so probability of n customers in the queuing system, average number of customers in the queuing system, average number of customers in the wait. Okay, average time a customer spends in the queuing system, average time a customer spends in waiting line. Okay, probability that server is busy and a customer has to wait, so that is called utilization factor. Okay, and probability that a server is idle and customer can be served, so 1 minus rho. So this is the way. So there are two. There you can see now we will all the equations. Okay, all the equations in the queuing model that will be writing based on two terms. Okay, will be writing based on two terms, and they are lambda and mu. Okay, when you see all the equations, yeah, even wherever the equation comes. Okay. So number of customers in the queuing system. Okay, number of customers in the waiting line. So L, LQ. Okay, W, WQ. Okay, then row. Okay, 1 minus row. So wherever you are entering the data, you can see to that everything will be based on two terms. One is lambda and other is mu. Okay, all the equations are based on the two terms. One is lambda and other is mu. What is lambda and what is mu? What is lambda and what is mu? So what is lambda and what is mu? Okay, so lambda is basically the mean arrival rate. Okay, so lambda is the mean arrival rate. Lambda is mean arrival rate or average number of arrival system in the queuing system per unit time. And mu is the service time. Okay, and mu is the service time. Okay, so based on these two terms only, all the equations, okay, all the equations in this queuing model, okay, queuing model will be writing. Okay, queuing model will be writing. Okay, so there are basically two terms you have to, you can see in the queuing system. One term one term will be always relates to the term called Q. Okay, so one term will always relates to the term called Q, and the other one will be always discussing with respect to system. What is the difference between these two terms? What is the difference between these two terms? Any guess? Any guess? So system includes, so queue includes only the queue, only the waiting person, only the waiting period. So that is the queue. So system includes your queue. Okay, normally the queue plus the one which is being served, the one being served in the system. Okay, one being served in the system. Okay, so wherever the system comes, if a person is inside your service discipline and if he is performing a task, So that if you want to include, you have to use the calculation part called systems. So Q only discusses or describes with the person who is waiting in want of service based on the service discipline. Okay, so you will terms like, so in the L you will have the terms like LQ. Okay, you will have the term here LQ, you will have LS, then you will have WQ. Okay, you will have WS. Okay, yeah. Right. Now, what is LS? So, LS is nothing but expected number of customers in the system. Okay. So, LS will be expected number of customers in the system. Okay. Whereas LQ corresponds to average or expected queue length. Okay, so average or expected queue length. Okay, so same way WQ is the average waiting time of a customer in the queue. Okay, so WQ is average waiting time of a customer in queue. Okay, whereas the term WS corresponds to average waiting time of a customer in system. Okay, average waiting time of a customer in system. Okay, so that is WS. Okay, and the equations we have already seen it over the. So LQ is LQ will be lambda square divided by mu into mu minus lambda to mu minus lambda. The WQ will be LQ by lambda. LS will be lambda divided by mu minus lambda, and WS will be LS by lambda. Okay, and there are some more terms are there. So as and when we are solving, we can see the equations. We can see the corresponding equations in that case also. So you can see. So everywhere you can see the terminologies. Yeah. So L is the LQ is the WQ. So here you can see the differences accordingly. Okay, so we'll solve a problem straight away. We'll solve. I hope the things are clear. Any doubt or anything to be discussed, we will discuss now. Then we'll straight away move into the problems. Yeah, anything to be discussed? Is the notation? Yeah. Yes. Which one? Lambda and mu will be given in the problem. The information to determine lambda and mu will be given in the problem. Need not to be
Sir, in the real case, for each person, the lambda and mu is different.
For each
person in the queue.
Yes. That
how can
yes.
we estimate the single
Exactly. You are right. That is the reason why we are not going for we are not taking that as individual times. We are taking that in terms of probabilistic distributions. Okay. So the probability distribution, we are taking it because of that reasons.
No, but sir, how can we take a single lambda and single mu? It will be different, no?
See, it is not, it is a single lambda and mu. So, okay, so I'll come to it. Normally, if you are doing any kind of project works or any these kinds of simulation studies in industry, so in industrial engineering, you might have studied the terminologies called time study, method study, and work study, etc. Have you?
Yes.
Yes?
No, sir. I don't know.
No. Okay. Okay. So when you are doing these kinds of work, you will be doing the study called time study initially. So the time study, normally what you will do is that you have to record the times. Okay, you have to record the times. Okay, for the part entry or the person entry by using the stopwatch. Okay, the time the inter arrived. So you will get first person arrived at a time like this. Second person arrived at a time like this. Third person arrived at a time like this. So likewise 10, 50 or hundreds of person entering into a system on per hour or per minute, etc. you will be recording. After recording it, okay, you can fit these timed data, okay, timed data into various distributions. Okay, the timed data you can fit into various distributions. Okay, and you can see to it where basically the minimum error is, the minimum statistical error is coming, okay, or the maximum fit wherever it is coming. For that particular distribution, that will be defined based on certain values. For example, if I take a triangular distribution, so it requires 3 values. Okay, if I take a normal distribution, it has 2 values. So likewise, that hundreds or 50s of data, you can find that which is best suited for that case, and for that particular condition, what that distribution requires, so that value you will plug in. Okay,
Sir,
there is a one minute. There is a software is that called Arena. So using that software, so you can able to tell you which is basically or how or which distribution it is basically fitting well. Okay, here for our simplicity, we are telling that the Markovian property we are taking and we are assuming it to be the inter-arrival as Poisson or exponential distribution. Yeah, now you tell me.
Sir, here, where are you taking the probability, sir?
Which one?
Like we need individual lambda and individual variance for calculating the curve of the probability, you know, the probability
Yes.
distribution.
So we are summing it up. We are summing it up.
Okay.
Okay, and how Arena works, etc. If you want to see, I cannot give that time here right now. If any free time is available, I can show you that how to fit that things in the Arena and how to get the distributions, etc.
Sir,
Yes, please.
sir, here it is given that average time customer spends in queuing system and average time customer spends waiting in line, sir. Sir, may I know the basic difference between those two, sir? Because
Which one?
between the first and the second, sir, that is the average time customer spends in queuing system and customer spends waiting in line. What's the basic difference, sir?
See, when you are waiting in a queue, okay, okay.
Yes, sir.
You are completely ignored about the person who is in the system and perform and getting his work done.
Okay, sir.
Okay, so queue includes only queue the person who are waiting in the queue alone. Okay, the
Okay,
person
sir.
who are waiting in the queue alone. and inline that includes the person who's being served also. So I have you seen my previous writings here? I have used here two terms. One is called queue and other is called system. So the queue includes only the queue time, only the average or expected queue length or average waiting time in queue. Okay, that includes only the waiting period in the queue. So in the system means you are waiting in the queue and you got a service, and the time from waiting to exit, what does it required, that statistics is taken as system here. It is mentioned in the PowerPoint as inline. Okay, you can see expected number of customers in the system. So in the system means that includes the queue and the person who is getting a service done in the server. So that is the difference between the queue and system here. So that is what is again shown over here as queuing system and inline. That's all.
So basically, the average time customer spends waiting in line means the waiting time, that is the waiting time in queue plus the time during which the customer is getting served also.
Yes, yes, exactly.
Okay, sir. Thank you, sir.
Yeah. Tell me how to proceed. So what is given?
Lambda and mu
So
both given there.
yes, so it is customers is arriving at a Poisson, so according to a Poisson process with an average time of 5 minutes between arrival, and service time of exponentially is distributed with a mean time of 2 minutes. On the basis of this information, find what would be the average queue length. So queue length, okay. What would be the average number of customers in the queuing system? Okay, what is the average time spent by a car in the petrol pump or bunk? What is the average waiting time for the car before receiving petrol? So these are the four things you have been asked to find. So we'll see how it has been proceed. So it is given as average inter-arrival. So the every 5 minutes, one car is arriving. So every 5 minutes of interval, one car is arriving to the petrol bunk. So you can find that the how many cars are arriving in an hour. Okay, in an hour. So per hour, so it is we'll go with the service rates, etc. So it is better to take with respect to hour. So we can see the lambda. So every 5 minutes, one car is arriving. So every hour, 12 cars is entering into the system. Okay, and average service time is again 1 by mu. So it is given as 2 minutes. So every hour. So every hour you are able to serve 30 cars in an hour in the petrol bunk. Okay. Was that clear? So lambda is 12 per hour and mu is 30 per hour. So every 5 minutes, one arrival. So every 1 hour, okay, you can see 12 per hour, and the mu is 2 minutes. So on an hour, 30 cars you are able to service. Now, what would be the average queue length? Okay, the average queue length is denoted by the letter LQ. Okay, denoted by the letter LQ. And LQ is lambda square divided by mu into mu minus lambda. Okay, lambda square divided by mu into mu minus lambda. So you can substitute the, okay, so you can, sorry. Yeah. So you can substitute the LQ. Okay. So LQ you can substitute there and you can get the time. So LQ. What is the next term which you want to find? In the next terminology which you want to find? What is the average number of customers in the queuing system? What is the average number of customers in the queuing system?
LS, sir.
LS. We'll see. Yeah. So next is average number of customers in the system is LS. Okay. Now what is next? Yeah, you are right. What is next? The average time spent by a car in the petrol bunk.
WS.
WS. Okay. Now what is next? What is the average waiting time of a car before receiving petrol?
WQ.
What is the WQ? Okay. Yeah. So you have determined that terminologies straight away by substituting in the equation. So you need to memorize. So you need to memorize these equations. Okay. So you need to memorize these equations. So this slide in between got scrolled off. So here the terminologies are given over here. Okay, so these terminologies you should know. These equations also you should know before solving the problem. Okay, so one we have seen. You can just have a look on the slide. So L is the number of customers in the system. It is given waiting and being served. LQ is the average number of customers in the waiting line, queue alone. W is the average time of customers spent in the system waiting and being served. WQ is the average time a customer spends waiting in. So don't confuse with the notations. Please follow any one notation only. Okay. If you are fixing the term Q always with respect to the Q alone, let it be like that. The other term you take it as S. Okay. LS, LQ like that you can take, or LLQ, WWQ, that's the way you can take. Okay. P naught is the probability of 0 customers in the system. Pn is the probability of n customers in the system. Rho is the utilization rate in the system. So one more problem, I'll just scroll like that. I'll share the slide today so that equations and terms will be known to you. Then in the tomorrow's class, 1 or 2 more problems I will solve and quickly will solve, and we'll wind up the queuing model. Yeah. So that is the example number 2. So question number 2. What you have to determine? Probability that the ticket counter is free, and average number of customers in the queue. What is it?
Sir, that is Pn, sir. 1 minus lambda by mu.
Probability that the ticket counter is free. Okay, so that is P naught. Yeah, okay, fine. The probability of a no customer in the system. So yeah, so P naught you have to determine for the first case. Second one, average number of customers in the queue.
LQ, sir.
LQ. Okay, so lambda is straight away given, mu is also straight away given, so you can substitute it. Okay, first is P naught you have to determine, next is LQ you have to determine. Okay, so what you have to determine, that you have to understand, and then it is simply substituting in the equation, you will get the result. Yeah. Problem number 3. Okay, so lambda is given 15 per hour. So mu service rate is 1 on every 3 minutes. So 3 minutes is the service time for every person. So an hour you can carry, yeah, mu is given 3 by 60, 20 per hour. So average number in the waiting line, average number in the system, average waiting time in the line, average waiting time in the system. All four you have to determine. Okay, so waiting line is LQ. Okay, now then you have to determine in the system as S. Okay, and in the queue and the line as Q, and in the system as S. So all the four you have to determine. Average number in the waiting line. Okay, yeah. So I'll stop here. So I'll give you 1 or 2 problems for you to practice. Let me see what to be. Yeah, okay. So before that, another one I'll give you. Yeah. So there's a problem is there on your screen. I hope my screen is also visible. Please let me know what to be calculated in each cases. Which term to be calculated on each case. What is lambda value? What is mu value? And please tell me what to calculate from the each term. Yeah, so patrons arrive at a reception counter at an average inter-arrival rate of 2 minutes. The receptionist in duty takes an average of 1 minute per pattern. Okay, so what is lambda and what is mu?
So it's lambda 30 per hour.
Lambda is 30 per hour. Okay, right. That is correct.
And it is 60, sir.
Lambda
Mu is
equals
60.
30 per hour and mu is, yeah, mu is 60 per hour. Correct. Yeah, right. Now for first question, what is the chance that the patron will straight away meet the receptionist? What is the first term to determine? What is the first term to determine?
P naught, sir.
Yeah, so P naught. Can you tell me what is the equation for P naught?
Lambda by mu, sir.
1 minus lambda by mu.
1 minus lambda by mu. Okay, lambda by mu is basically the service rate or the server busy time. So 1 minus lambda by mu. Correct. Now, next thing. What is the probability that the receptionist is busy? What does it?
Lambda by mu.
Pardon me? Yeah, that is lambda by mu. So PB, so PB equals 1 minus P naught. So that is lambda by mu. Right. Next one. Next one. What is the average queue length?
LQ.
LQ. What is the equation?
So lambda square divided by mu of mu minus lambda.
Mu of mu minus lambda. Right. Now, next thing. What is the average number of patrons in the system? Next one. What is the average number of patrons in the system?
LS.
LS. What is the equation?
Lambda by mu minus lambda.
Lambda divided by mu minus lambda. Okay. Next one. What is the average waiting time of a patron?
WQ, sir.
WQ. Correct. You have to calculate WQ and the equation is
Lambda by mu into mu minus lambda.
lambda divided by mu into mu minus lambda. Right. Next one. What is the average time a patron spends in the system?
WS.
WS. The equation is
Lambda by lambda into mu minus lambda.
okay. So I can simplify it and write as
LS by lambda.
yeah, 1 divided by mu minus lambda. Okay, G. If the average waiting time of the arrival exceeds 1.5 minutes. So what information is given and what to determine? what information is given and what to determine. So what is given? When the average waiting time of an arrival exceeds 1.5 minutes. What is average waiting time of an arrival? Average waiting time of customers. So what term is used here? WQ. Am I right? So WQ is given. So WQ equals lambda divided by mu into mu minus lambda. Okay, so WQ is given as 1.5. Okay, 1.5 by 60, since everything is we are taking in hour. So 1.5 by 60 equals lambda divided by mu is 60. So 60 into 60 into 60 minus lambda, and you can determine the new lambda. So the new lambda will be 36 hour. Okay, new lambda will be 36 hour. So that is equal to 60 by 36. So 1.67 minutes. Okay, clear. So if you solve the problem, you have already written the equation, lambda and mu also I have written over there. You can substitute and solve. So when you want substitute it and solve, you will get the values. So P naught is 0.5. You can verify. P naught equals 0.5. PB equals 0.5. Sorry. PB equals 0.5. Then LQ value is 1 by 2. Then LS is there. So LS, the value is 1. Then I have W. So WQ equals 1 minute. And WS equals 2 minutes. So data, the last question I have solved over there. Okay, so the issue here is that you have to just know the equations. You have to memorize the equations for solving it. Once you know the equation, only thing is that you have to identify what to be determined by each term, and accordingly you can calculate and you can solve the problem. So one more we'll try. Yeah, that's the next question. Yeah, so what data is given? What data is given and what has to determine. So the machines in a production shop breakdowns at an average of 2 per hour. Non-productive time of any machine costs rupees 30 per hour. If the cost of repairman is 50 per hour and the repair rate is 3 per hour, calculate the number of machines not working at any point of time, average time that a machine is waiting for the repairman, cost of non-productive time of the machine operator, expected cost of system per hour. Okay, so what is lambda given here? What is lambda here? What is the value of lambda? Lambda is 2 per hour. Am I right? And mu, what is mu here? What is mu here? Mu is 3 per hour. Okay, the rest data, let it be there. We will take it on a later time. Okay, now lambda and mu is got. Now what is the first term to determine? What is the first term to determine? Number of machines not working at any point of time. Which one? Number of machines not working at any point of time. Which term? LS or LQ? Since it is number. L, length. Length of Q or length of system? LQ or LS? What is that? So that will be LS. Okay. Since it is given as at any point of time. Okay. Any point of time means at a particular time, the machine which is waiting in want of service plus the machine being serviced. So that is also not working. So you have to calculate LS, the length of system. Second one, average time that a machine is waiting for the repairman. Average time that is a machine is waiting for the repairman. So that is the waiting time in the queue. So that is WQ. Third one, cost of non-productive time per hour. Cost of non-productive time of the machine per hour. Okay, so I'll come to it. So LS, you know the equation. What is the equation of LS? Lambda divided by mu minus lambda. When you substitute and solve, you will get it as 2 machines. You will get it as 2 machines. When you solve for WQ, the equation is lambda divided by mu into mu minus lambda. The equation will be 2 by 3 hour. Okay, so you can, the third one, C. So cost of non-productive time of the machine per hour. So that is average number of machines not working at any point of time. So the third one. Okay, so to determine that, you have to find average number of machines not working at any point of time multiply by machine hour rate. Okay, so the so the average number of machines working at any point of time. So what do you have to determine? What you have to determine? Tell me. You have to find LS. Okay. So LS into machine hour rate. Okay. That is LS into machine hour rate. So LS is already we have determined, it is 2. Okay, so 2 into machine hour rate. So machine hour rate is already given in the question that the non-productive time of any machine costs rupees 30 per hour. So 2 into 30. So that is rupees 60. Okay, rupees 60. Now what's the next thing? So number 4. So number 4 is expected cost of system per hour. So the term is TESC. So TESC equals cost of waiting per hour. Okay. Cost of waiting per hour plus cost of service per hour. Cost of service per hour. So cost of waiting per hour we have already calculated 60 plus idle time cost is already given. The cost of repairman is rupees 50 per hour. Okay, so 60 plus 50, that is rupees 110. Okay, so this is cost. C is basically the cost of waiting per hour. Okay, cost of non-productive time. So that is basically the cost of waiting per hour plus cost of service per hour. So 60 plus 50 rupees 110. Okay, so this is how the problems in the queuing theory we have to solve. So any doubt or anything to be cleared, we will discuss. We'll quickly go through the remaining problems in the PowerPoint. So problem 1, 2 and all we have seen on yesterday. Yeah, so this is also I think I discussed with you on yesterday. Average number in the waiting line. Okay, which term has to find? Average number in the waiting line. Which term we need to find? Average number in the waiting line. So LQ we have to find average number in the system. So we need to find LS. Average waiting line, average waiting time in line. So that is WQ. Average waiting time in the system, that is WS. So you know the equations, you can substitute it. Okay, you can substitute it and you can get the answers. Answer part is also given here. Yeah, next one. So Sari Emporium has a single cashier. During the rush hours, the customer arrive at a rate of 10 per hour. The average number of customers that can be processed by the cashier is 12 per hour. On the basis of the information, find the following. So lambda is 10 per hour. Lambda is 10 per hour and mu is 12 per hour. Okay. So the probability that the cashier is idle. So you can find the traffic intensity rho, that is lambda by mu. Then average number of customers in the queuing system. Okay. So that is system. So that is LS. Average time a customer spends in the system. So that is WS. average number of customers in the queue. So that is LQ.
Sir, first one 1 minus lambda by mu.
Pardon me?
First one 1 minus lambda by mu, no, sir.
No. No. Why? The customers are processed by the cashier. Okay.
Server is idle.
Yeah, server is idle. Correct. So it is 1 minus lambda by mu. Correct. Okay. So yeah, that is 1 minus lambda by mu. Correct. Sorry, not the yeah, correct. Okay. Now the average time a customer spends in the queue. So that is WQ. So once this is not, the equations are not, you can substitute it and you can get the required information. Yeah, so that's the last one. The arrival rate of a customer at a banking counter follows Poisson distribution with a mean of 45 per hour. Service rate at the counter clerks also follows a Poisson distribution with a mean of 60 per hour. So lambda is given. Lambda is 45 per hour and mu is given 60 per hour. What is the probability of having 0 customers in the system? What is the probability of having 5 customers in the system? What is the probability of having 10 customers in the system? So you have been asked to find the probability. Then you have find LS, LQ, WS and WQ. So that you can determine. So how to approach the first one? 0 customers in the system. What is the probability? It is not asked for anything else. It asks for the p values, the probability values. So how to determine it? We'll see. Yeah. So how to determine it? What is the probability of having 0 customers in the system? So how will you determine it?
Sir, is it 1 by 4, sir? Is it 1 by 4 answer, sir? The probability of 0 customers.
How?
Lambda it is given 45, sir. Mu is 60. So P naught will be like 1 minus lambda by mu, no, sir?
Okay. You have to, what is the probability of having 10 customers in the system? So, okay. See, for determining that, there are 2 equations are available. Okay, so I'll just scroll back. Yeah, so you can see the equation here. So, so probability of n customers in the queuing system. So that is Pn equals lambda by n, lambda by mu to the power n into P naught. Okay, lambda by mu to the power n into P naught. So the equation is given lambda by mu to the power n into 1 minus lambda by mu. So this equation you have to apply it over there. Okay, you have to apply this equation over there, or else you can use that, or else I'll just modify that equation. Okay, so that is lambda by mu into e power minus mu minus lambda to the power n. Okay, Either this equation or the other equation you are using, you will get. Can you substitute? Who told me the answer as? I didn't remember that value. What was you told? You have calculated P naught. Yeah, that's fine. Okay, it's basically from the P naught only it is determining, as you can see over here. Okay, so this is lambda by mu to the power n into P naught. Who gave me the answer? Can you substitute it and get me the result?
One by 4, sir, for 0 customers.
1 by 4. So somebody has earlier, who told me earlier?
Sriram, sir.
Sriram, are you not there in the, are you not there? Yeah, okay. So this is how you
Sir,
have to. Yeah,
sir, I'm here,
Sriram.
sir.
Yeah, so that is 1 by 4 only.
Hello,
It is
sir.
coming. Yeah. Sriram, it is 1 by 4 only coming.
Yes,
but
sir.
this, but this is how this is the straight away the equation
For 0 customers, it is I guess 1 by 4 only, sir.
for 0 customers.
Okay, sir.
Yeah, for 0 customer this is 1 by 4. So this is the equation you can substitute. Either this equation, okay, either this equation,
sir, understood, sir.
either this equation, or you can modify into this equation. In any one of the equation, you can substitute it for the case. So n is 0 here, n is 5 here, n is 10 here for the cases. Okay. Whatever you told is right. Whatever you told in your calculation, that is also correct. Okay, so this is how we are solving it. So one more problem is that I am not substituting anything over here. You can work out for this problem. Okay, so was this clear? Was the topic clear?